Hi and welcome to video 7 of this series on normal distribution, Unit 4, Topic 4 of the Math Methods curriculum. I'm going to talk to you today, the last video of this topic, normal approximation of the binomial distribution. Well, the last video, of course, assuming that I get through the examples and keep it under 10 minutes. Otherwise, I'll break it into 2 videos. So, consider a binomial distribution. We've seen quite a few. These were in Topic 3. If it's a reasonably large data set, n, so there's a large number of trials in terms of binomial, and p equals 0.5, it will look like a normal distribution. There will be a lot of data in the middle, less on the outside. So for, rolling a dice 100 times, you would expect to get a 6 16 times, or to get an odd number 50 times. And if you did this a million times, 50 would happen up the most, but you might get 49 or 51 sometimes. You might get 40 odd numbers and 60 even numbers once. And these things might happen, but it's going to be approximately normal. So we can use a normal distribution to actually do an approximation on the binomial distribution. As long as n is large enough, this can even be true for skewed values of p. So p doesn't have to be 0.5. In fact, p can be 0.1. As long as n is large enough, we can still use a normal distribution to help us approximate. So the general rule is that for whatever p is, the number of data points that we take, the number of samples n, so the general rule is that for whatever p is, the number of data points or samples, n, times by p, should be greater than 5, and n times by q has to be greater than 5. So obviously if p was 0.99, well, n can be quite low, but then nq is going to be the problem. So then n has to be large to account for that. So if p is 0.99, that's also a really skewed set of data. But we can approximate with the normal distribution based on this criteria. It's just a criteria that's been set randomly. There are other people that will say it has to be greater than 10. Other people might say it has to be greater than 2. So it really depends on the situation, but this is a good general rule of thumb to use. Now we know also that BNP implies that Q, the probability of failure, is equal to 1 minus P, and we've got N mu sigma, but that should be sigma squared, is such that we get this. This is really important, and you won't have seen this. Mu is the expected value, and it's equal to n times p. You've seen that before. But sigma squared, the standard deviation or the variance, can be calculated by doing n times p times q. So this is going to be the thing that you need moving forward. And of course, then sigma can be calculated by doing the square root of that. So you'll need to know sigma for your actual normal approximation. So let's have a look at one. Given that x is approximately a binomial distribution with 1,000 trials and the probability of success is 3/7, determine the probability that you'll get success 500 times. So it's greater than 500. Now this is a discrete distribution, so we're actually saying greater than 500 means that we want it to be greater than or equal to 501. So I've just written 500. So you have to really be thoughtful about this because it's discrete. We don't have 500.01 or 500.6. We only have 500 or 501. In a normal distribution though, remember normal is continuous, we will actually be calculating the probability that x is greater than or equal to 500.5. Because in that continuous representation of the binomial situation, if we got an outcome of 500.5, that would round up to 501. So there's always that little bit of analysis to do at the start to make sure that we map our continuous against our discrete appropriately. And we are always going to be working on half a value below or half a value above, depending on the question. So we want to calculate, first of all, first we want to check this. NP is equal to 1,000 times 3/7, which is about 420, but I better calculate it. 1,000 times 3 divided by 7 is 429, we'll say. So that's 429. So that's greater than 5. Excellent. And NQ is equal to 1,000 times 4/7. So this is even larger, which means we don't really have to write this down, but I'll do it anyway just to show you. Times 4 divided by 7. And this is 571 approximately. So we're all good to use the normal approximation. So we're saying that if x is approximately equal to b, then we can say that mu is equal to np, which is equal to 429, but we might be a little bit more accurate since this is part of our calculation. So if I go back here, it's 428.57 is a better way of doing it. And we're going to say that sigma is equal to the square root of npq, which is equal to the square root of 1,000 times 3/7 times 4/7. And let's do that calculation. So shift square root 1,000 times 3/7 times 4/7, and that's equal to that, but I might keep it as a rounded value here, 15.65. So 15.65 is our value of sigma. I'll just give myself a little bit more space here. So therefore, our probability that x is greater than 500, and this is discrete, is going to be approximately equal to our probability that x is greater than or equal to 500.5, which is continuous. And for that I've got my mu and my sigma, so I'm going to be doing n normal CD. My lower bound will be 500.5. My upper bound will be 1,000 because that's the most I can get, so it's far enough away. My standard deviation is 15.65 and my mean is 428.57. Okay, remember all those numbers and shout at your computer for me. I exit here. I shouldn't have done that. Oh no, I didn't need to do that, sorry. Stats, distribution, normal, NCD. I want to go from 500.5 to 1,000, and I've got 15.65, and then I've got 428 and this is where I've fallen down, 2957, not anywhere near 29. Close brackets, enter, and that's giving me a value that's quite low, which makes sense because our probability of getting to 500, well, this is standard deviation, and that standard deviation is implying that it's quite a compact set. So 500 is actually, so that's 70, so 5 standard deviations above. So this probability is actually equal to 2.1516 or 17, 2.1517 times 10 to the power of negative 6. 2.1517, 10 to the power of negative 6. So we expect it to be quite low. So now I just need to ask you, who is the coolest doctor in the hospital? The hip doctor. That's right, you keep laughing. Anyway, I haven't actually done example 12. I did do it, but I've decided not to include that part of the video. It worked out to be 0. Because it had a low standard deviation and I hadn't really tested the question, the spread didn't carry through to the question. And there are going to be a lot of questions like that. There are some additional examples here though in exercise 17E, so I suggest you have a look at those, and then you just really have to follow the rules that are available. And you'll find that most of these questions work, certainly the ones that are written for your exams. Any questions you have, make sure you bring them to your teacher. All the best.